Hello everyone, in this tutorial we'll be going over a simple NACA0012 airfoil and running getting some results with an unstructured grid. This will give inaccurate results, but might be a good starting point for more accurate simulations or an argument for using structured grids instead. So here are the files for this case. We have the OpenFOAM mesh case files, a clean script just for your convenience after you've run a simulation and you want to remove every generated file. The mesh written in GMSH, or Gmesh as I pronounce it. The Readme, which contains all the commands that will be run in order to go from start to finish. And this is a script that is part of the simulation, not the entire thing though. And these are some sample results that I'll show later, comparing experimental data with the results we get here. So let's take a look at the README. Here you can see. So first, I've set up the mesh so that it's parameterized on the angle of attack, so you can quickly switch angle of attacks and rerun the simulation to get lift and drag at different angles of attack. And then after that, we just generate the mesh we can do it through the command line or through the GUI. I'll go through the GUI later to show the mesh. And then we run the run script that I had, and we'll take a look at what's inside there as well. And finally, we can view the post-process results in ParaView and look at the force coefficient data. Alright, so first let's take a look at the mesh. You can see it's a simple unstructured recombined mesh. Unstructured grids are usually have triangular cells, but Gmesh has this recombination capability where most of the cells will be made into quadrilaterals. And here you can see it gets finer near the airfoil, and you can see like most of these cells are quadrilaterals. And yeah, this is a rather coarse mesh. It probably would not be good enough to resolve the boundary layer, but we're just going to try and see what kind of results we get, just because they generate results quickly. Okay, so after that, let's take a look at, after you generate the mesh through the gmesh command, you'll be running the run script as I indicated before. And here we have the conversion utility. This is from the Gmesh format to OpenFOAM. And here we have, it's more of a, when it's freshly converted, you still need to make some changes, and OpenFOAM has this nice utility to do that for you. And here is finally the actual simulation. Simple foam is a steady state algorithm using the simple algorithm. And yeah, so that's pretty much it. I'll just run run the case for you. I won't do it till completion because it does take a few minutes. Actually, no, it's going to take a while to generate the mesh. But yeah, let's just go ahead and get to the results, sample results. So here we have the blue is experimental data I got off of a NASA website. The red and yellow are simulation data. So as you can see, it's not bad in the lower angles, but as you approach the stall point, our course grids results diverge greatly from the experimental data. You can ignore these at the bottom here. This is just for some reason it wants to plot these zeros as these empty in these empty slots. I didn't simulate all angles for every grid. I just took a few points to see the difference. And the drag results are even more off. Well, actually, it seems like the computational results kind of get close to the post-stall region too soon. So you can kind of see this here and here as well. They're pretty close to the stall values, but for the drag values, they're still quite high compared to the experimental results. Now there are many ways to try to improve these results. You could use a finer grid, you could use a structured grid near the boundary, and you could also play around with the numerical schemes in the FV solution and FV schemes configuration files in the OpenFOAM case files. But I won't be going over that in this video. Well, that's pretty much all there is to it. If you have any comments, suggestions, or questions, please let me know in the comments. Thank you for watching.